The event was logged as the pinprick, a laughably inadequate name for the catastrophe that followed. On July 14, 2045, at exactly 4:03 Greenwich Mean Time, the Earth registered an impact, not a large, catastrophic asteroid, but a single, microscopic grain of silicate sand, traveling at 99,999% the speed of light. It was the definition of mass energy equivalence made horribly manifest. The energy released was equivalent to 1024 joules, or roughly 240,000 megatons of TNT, 20 times the yield of all nuclear weapons ever built. It struck deep in the unpopulated South Pacific, not far from the Challenger Deep. The initial shockwave was not an explosion, it was a silent, instantaneous vaporization of an entire segment of the ocean floor, creating a temporary, kilometers-wide pocket of superheated plasma where water used to be. The real damage, however, came from the secondary effects. The immediate result was a flash-boiled mega-tsunami that erased coastal cities around the Pacific Rim in minutes. The atmosphere, instantly superheated and displaced over the impact zone, launched an ionization wave that permanently fried every unprotected satellite, crippling global communications and navigation. For those of us who survived the initial chaos, mostly inland dwellers like me, Dr. Alan Reed, a seismologist, the world had become dark, silent, and disconnected. But the most insidious effect was seismic. The colossal energy transfer didn't just displace the water, it delivered a hyper-localized, kinetic punch deep into the mantle. Our early seismic readings, before the power grid sputtered, showed a massive, sustained vibration. It wasn't the kind of shockwave that dissipates, it was a rhythmic, unnaturally stable oscillation of the entire planet's interior, humming like a gigantic, distressed bell. We evacuated our university lab and retreated to a shielded former Cold War bunker, determined to continue monitoring the planet's death throes. As days turned into weeks, the global surface seemed eerily stable beneath the new layer of communication silence. The tsunamis had receded, leaving behind a ruined coast. Yet, the persistent seismic tremor intensified. My colleague, Dr. Eva Hess, noticed something crucial in the geological data we salvaged. The Earth's rotational speed was decreasing, slightly, immeasurably slow to human perception, but undeniably slowing down due to the constant, internal vibration. We initially theorized the impact must have created a massive, internal magma countercurrent, acting as a planetary brake. The slowing rotation, combined with the loss of satellites, made time and space confusing. Days stretched imperceptibly longer. Worse, the sustained internal friction was heating the planet from the inside out. Within 6 months, volcanic activity surged worldwide. Giant fissures opened in tectonic plates, belching steam and ash. The surface became increasingly inhospitable, forcing more survivors underground into old mines or military installations. The final, terrifying piece of data arrived 8 months after the pinprick. Eva and I had managed to re-establish limited radio contact with a deep-core drilling station in Siberia. They confirmed our fears, the planet's slowing was accelerating rapidly, and the core temperature was spiking. But their last transmission contained the true horror. They had bored directly into the epicenter of the sustained internal vibration. It was no longer a vibration. The impact had not merely created a ripple. The hyperrelativistic grain of sand had transferred its energy so completely that it had instantaneously vaporized the surrounding rock and, against all probability, stabilized the resulting energy into an object of impossible density. The Siberian team called it the permanent cavity. This cavity, deep in the Earth's mantle, was not empty. The incredible pressure surrounding it was causing the surrounding rock to collapse inward. But due to the rotational slowdown and the massive internal friction, the collapse was not uniform. The Earth was effectively consuming itself, pulling its mass towards this zero point of impact. The unexpected twist lay in the origin of the sand grain itself. Eva, desperately cross-referencing astronomical data, stumbled upon a pre-pinprick anomaly, a minute but powerful gravitational distortion detected briefly near the Kuiper Belt, a region previously theorized as a potential site for primitive, non-biological mega-engineering. The distortion was immediately dismissed as sensor noise, but now it made a terrible kind of sense. The pinprick was not an accident. The immense energy of a lightspeed impact had been perfectly calibrated to initiate the planet's internal destabilization. The grain of sand was merely the payload. Eva's frantic calculations, scrawled on the bunker walls, revealed that the slowing rotation and the thermal spikes were the perfect conditions to bring an entire planet to a halt, essentially curing its rotational and internal energy for a truly massive, extraterrestrial resource extraction effort. The deep, rhythmic oscillation wasn't a death tremor, it was a colossal planetary braking mechanism. We had been perfectly targeted, not for destruction, but for harvesting. As the final tremors began to shake the bunker, tearing the reinforced concrete apart, Eva whispered her last, chilling realization: the energy required to accelerate one grain of sand to that speed. It would be easier to just accelerate all the mass of the solar system. Unless they didn't want the planet destroyed. They wanted it stopped. The last we heard was the Siberian team's transmission cutting out, replaced by a sound that wasn't a tremor, but the deep, grating screech of two massive tectonic plates locking against each other as the planet finally ground to a terrifying, absolute halt. The pinprick hadn't destroyed the Earth. It had merely set the parking brake for an alien salvage crew.